In section 7 of chapter 4, we're going to talk about the stoichiometry of precipitation reactions. So let's start with 10 milliliters of a 0.3 molar sodium phosphate solution reacting with 20 milliliters of a 0.2 molar lead nitrate solution. Let's first start with a balanced chemical equation. What precipitate will form, and then we'll find the mass of the precipitate that will form. Here's our balanced chemical equation. Lead 2 phosphate is our precipitate. Remember, all sodium compounds are soluble and all nitrates are soluble, so the other product is not our precipitate. Next, what mass of precipitate will form? Well, we have information about both reactants. This is a limiting and excess reactant problem. We have to find that limiting reactant to predict the mass of precipitate that will form. So using the volume of the sodium phosphate, we'll get to moles. So we can do our mole ratio, switch between the sodium phosphate and the lead phosphate. And then lead phosphate has a molar mass of 811.54 grams per mole. 1.2 grams for that first reactant. For the second reactant, 0.2 molar, 20 milliliters. We're in a 3-to-1 ratio between that reactant and the precipitate product, and we get 1.1 grams. So that means that our lead nitrate solution is our limiting reactant, and we should get 1.1 grams of precipitate produced. Now to some more advanced questions. Same scenario, same reaction, same set of solutions. What is the concentration of the nitrate ions left in solution after the reaction is complete? Nitrate ions are not part of the precipitate. They are spectator ions. And so, you're at 0.2 molar and 0.02 liters. Solve for your number of moles. 0.0040 moles. But for nitrate ions, we have a subscript of 2 in our chemical formula. So we have 0.0080 moles of nitrate ions. But we want the concentration, we want the molarity. Once we put the two solutions together, we're going to have a total volume of 30 milliliters. So in liters, 0.03, and that gives us a concentration of 0.27 molar. That's the concentration of the nitrate ions after the reaction is complete. The same number of moles, but now in a larger volume because we've added the two solutions together. Now to something a little harder. Same scenario, same reaction, same solutions. We want the concentration of the phosphate ions left in solution after the reaction is complete. Well, we said on a previous slide that the lead 2 nitrate was the limiting reactant. So that means the sodium phosphate is the excess reactant. And phosphate ion went into the precipitate, so it's a reacting ion, not a spectator ion. If this phosphate ion was the limiting reactant, this problem would be really easy. We would say the concentration of the phosphate ion, if it was the limiting reactant ion, would be 0 after the reaction is complete. But it is an excess reactant ion, so it's going to take a little bit more work. So initially, we have a 0.3 molar solution, 10 milliliters of it, and so we have 0.003 moles of sodium phosphate. Now let's think about how many moles of sodium phosphate actually react. So with an excess reactant, some of it reacts, some of it's left over. Start with your limiting reactant. So our limiting reactant's the lead nitrate solution. Find the moles. And looking at our balanced chemical equation, 3 moles of lead nitrate for every 2 moles of sodium phosphate. So 0.0027 moles of that sodium phosphate actually react. So the difference is 0.0003 moles. And now that is in a total volume of 30 milliliters again, so 0.03 liters. That gives us a 0.010 molar concentration. And that is also the concentration of the phosphate ion, because there is just one phosphate ion in our chemical formula. So now give these problems a try, and we will whiteboard them tomorrow.